please thank you everyone for joining, and please jump in with questions when you have them. I'm a little bit of a nervous presenter, and so you know, questions every so often do certainly help me. So this paper, I was drawn to this paper on the title, and then the more I looked at it, the more I liked what it was doing. So broadly, what it is concept whitening, which is it allows you to learn a CNN, and then while you're learning the neural net CNN, you can bake in concepts that you define and that you're interested in. And then the concept of whitening that they refer to comes down to the fact that they are trying to disentangle the weights and different levels in a particular layer in the neural network, trying to disentangle concepts across those nodes to be quite pure and held in a single node. So how will I describe this then? Where will I go through first? Okay, so there have been various attempts at interpretability on neural networks before. Generally, it's on post hoc after the network has been trained, then trying to work out which nodes activate under which labels or classifications. But this has the problem that the neurons are not pure, and we want to try and make them pure, and this paper has an attempt at doing this. They work through various other works in this field, and then they start introducing their topic, which they are calling concept whitening. Whitening is a technique that's been used generally in neural networks and machine learning to normalize the signal across, say, different colors, so that each color becomes in the full range. This is using an analogy, and then so therefore the brightest color would become white. So it will take away a blue tinge, say, as you know, everything as the reds and greens are all also pushed out to white. The brightest image would become white. So they've used that analogy in the term whitening. So the earlier work in the area doesn't really impose restrictions on the latent space, whereas this one does. And they go on to say that the algorithm that they've developed, and they've released their code as well, can be used in place of batch normalization in a CNN, and usually with just a single extra epoch of training, you can get some very useful information out of an already trained neural network. So from that point of view, I think it's very, very powerful. So
Wayne, sorry, can I interrupt? There is a question here in the QA section.
Right.
I assume you didn't see. How is activation of a node defined? Large positive value.
Yes, yes. A large
Yeah.
positive output value is defined as used as how activated a node is. Yeah.
Cool.
Okay, so then I've marked this up with the various random thoughts that I had while I was reading it. So some of them are irrelevant now, and some of them, you know, are still pertinent. So another key thing that surprised me was that the concepts used in the latent space that we're interested in don't need to be the labels in the classification problem. We can have a different set of concepts that we're building from. And they're taken from an auxiliary data set which does have labels, an auxiliary data set that has these labels in it, if that makes sense.
So you have to already know sort of what kind of concepts you would be expecting to come out of it.
Absolutely. You absolutely need to know the concepts beforehand. And so they go into some examples, two sets of examples later on, which are quite good. Accelerated thing. Okay. And so one of my comments here was that in this work, they use a few number of concepts. So one of the pieces of work is 3, another is 7, and another is 80. So relatively to the concepts that you could have in an image, to me, these felt like very small numbers. Yeah. Explanation of my work. Okay, so they say some of the limitations in the other works. The fact that if you don't if you don't put a restriction on the concepts purely, you get the smearing across all the nodes in a layer, and the concept, you don't have a pure concept node in a particular layer. Then, okay, whitening and orthogonality. Okay, so what we're doing is we're in the latent space of a particular layer in a neural network. We're trying to disentangle the different nodes across that layer so that they are so they represent certain nodes that we know of, represent certain concepts that we are interested in. There will be more nodes that we don't have concepts for, or that pass extra information through the network. So I think there is a built-in assumption that the layer size is far greater than the number of concepts that you're looking for. So it starts talking about the orthogonality of the whitening, and that batch normalization generally uses the standardization part of whitening, but not the decorrelation. So this is the part they start attacking. So the difference is that they are taking the whitening matrix and they're multiplying it by an orthogonal matrix that maximizes activation along particular axes in the latent space. And there's a little example later on of this. They say that they brought parts of this. There are computational difficulties with with doing this, and so then they go into the types of savings that they've done in order to save computation and make it tractable. One of them is this transformation here, which I was meaning to go into in more depth, but I haven't yet. So apologies. Does anyone on the call know about the Cayley transform and curve linear search algorithms? No. Okay. So the methodology here is that essentially we're mapping the inputs through a latent space Z and then to the outputs. We're breaking this down into two parts such that we have essentially we're going to end up with 2 training data sets. One of them that is training the normal data set as you would train it. The other one has our concepts in it and is used in the whitening procedure. And an example of what they're trying to do in a particular node is this. So in A, if you have a particular node, or actually this would be 2 nodes because we've got 2 dimensions and we've only got activation 1. So if we've got 2 nodes, we can have our concepts can be represented, multiple concepts can be represented in a 2-dimensional space. So we can push them, center them on the mean. We can then normalize them. But what this paper does is the next step is it takes one of these concepts and it aligns that with this axis on this for this particular node, if that makes sense. Okay. They keep going on about how, then they start to explain how the current batch normalization is rotation free and that you don't get any alignment here going on. So this is what they add. I'm not sure if I should go through the maths or just drop into the algorithm. The algorithm has two phases to it. So at a forward pass, it is doing some, it is doing the ZCA whitening, and it's collecting information. And then the second algorithm that performs. Sorry, what does it do? So this is the one that does the disentanglement and the rotation.
So these orthogonal matrices, they are for the whole data set, or they are on the batch?
They are on the whole data set. My understanding is they're on the whole data set. But then you have two data sets. One that is your standard data set for going ahead and training your network, and the other data set that has your concepts in it that you want to align to. And so then you will say, essentially, in a layer of a network, you might have 70 nodes in it, and you might decide node 0 in a particular layer relates to aeroplane, node 1 cat, node 3, something else.
Yep.
So I might actually, rather than go through that, they do have the code, which I've downloaded, and I was planning to try and get that working tomorrow. So I'm going to be bad here and just jump ahead essentially to the experiments. What they're doing is they've set it up in such a way that they can produce concept whitening with a single pass, a single epoch on an already trained network, which is great. It replaces the batch normalization component. It is more computationally expensive than the batch normalization, but it does perform normalization in itself, so you can use it in place of batch normalization, if that makes sense. So what they start doing is they start going down, and so they alternate. As if you're training a neural network from scratch, you alternate between the two procedures. If you've got a pre-trained network, then you alternate between these two algorithms. The first one is whitening, and the next one is doing a what's the correct word? Is rotating, doing the rotation, and the unsmearing, trying to concentrate the activation of a particular concept in a particular neuron. So here what they've done is they've replaced the second layer of a CNN, so on images, the second layer, batch normalization with context whitening. They then take they have placed these, they've shown the network these images, and then they're plotting here the which concept was most activated in the second layer. So for these images here, the aeroplane most activated on this image, then this, then this, then this. Bed in a descending order down here, person descending order here. And then in the 16th layer, this is the kind of results that they got. So you can see that in the second layer of the neural network, the aeroplane concept really wasn't showing aeroplanes. It was being activated on images that were just sort of blue and maybe with some black or white highlights in them. Okay, cool. I've got a question. I will pause and just take that. This experiment made wonder, why did they only place one concept whitening layer in each network? If it is supposed to be equivalent to batch normalized, wouldn't it be better for all the layers? Excellent question. You're absolutely right. They do. But what they wanted, I think what this experiment is doing is they're trying to determine what it is doing. So they're using this just as an example. Later on, there are more examples where you can see the progression through a network. So this is trying to show that a concept is, if it is at every layer through the network, that it doesn't have equal weight all the way through the network or equal utility for us to understand what's going on. In layer 16, the airplanes are very airplane-like, the beds are very bed-like, the people are very people-like. So that's good. Back down on the second layer, it's almost colors and textures that it is trying to find, which does fit with our understanding of what the lower layers of a convolutional neural network do. And so here what they're doing is another experiment, they're trying to look at the trajectory of concepts in different layers. So, okay, I'm going to jump forward to the next graph here. So here what happened was they have taken two concepts just for the ability to explain what's going on. And then as they've moved through the network, we've moved through different layers, this image here activated the different concepts to different amounts. So in layer 2, this was very high on aeroplane and very low on bed. As it went through the layers, it started to become more and then less important for an aeroplane, or aeroplane was less associated with it, and then it became very strongly associated with bed. Whereas the sunset photo started off here being very strong with bed, possibly because of the warm colors, and so that would match what we saw in the earlier examples, and then it slowly moves towards quite high in the aeroplane dimension. Okay, what other experiments did they do? Then they did this one here, where they started to show that and I think they've got some of the descriptions wrong, and that they said this axis runs the other way. They started plotting images based on how each quartile or each bin of how strong they're associated with this, with a random image from that bin. And so here we see that as the bed concept is activated more highly, we do get beds down here. As the person concept activates more highly, we do see people. And they do note that a person in a bed is like in the intersection where you would kind of expect it to be. I was lost a little bit in this image here, and I think they're saying that the origin is this is the origin, and that most of the images actually cluster in this kind of area here, and that so that for the majority of the data set, they weren't really beds or people, and so you just got a low activation, which seems reasonable. Just over to this one. They started to look at interesting concept similarity. So they started to look at the different ways that you can. Is this one 16 class? They're trying to see the correlation of the different images, sorry, of the different concepts C is the 16th layer, a 16th layer batch normalization. Okay, so these two are batch normalization, and they show that they're saying that the activation between different the images of different different concepts is still highly correlated, whereas in their with concept whitening, this correlation drops right away. So you start to see that if the neurons that are activated for person are activated for people, and the other concepts are not highly activated. So they're saying that this is showing that the disentangling of the concepts is working. Concept importance, and then they go, they carry on here with, they compare batch normalization with their concept whitening again, good results that way. And then here they start to show images of the actual activations of different, so this is the class of object, the class label of the object in the learning set, the training set or evaluation set, where they have stables, libraries, boats, bedrooms and airfields. And then the concepts that they've learnt are similar but not the same. So they've learnt horses and books and boats and aeroplanes. And you can see that in the stable images, that a horse is a concept that is repeatedly has high activation, and same with an aeroplane for an airfield, which again is good.
I think there are some questions in the Q&A
okay,
in the chat.
Sorry, I've scrolled down too far. Yes, one more question. For the activations calculated for these figures, did they take the dot product between the whitened latent space representations of the data point and the unit vector associated with the concept? And I would have to go back, and I'd have to look back through more closely at the maths. I do not remember off the top of my head. So did they take the dot product between the whitened latent space representations of the data point and the unit vector associated with the concept?
Yeah, sorry, this is Peter, the one who asked the question. No worries if it's if you don't know, because like it is a pretty specific question. I was confused. I was thinking about how are they comparing activations from previous methods versus activations in this one, and how similar they are. Because an activation of a node seems pretty different than like the activation of a concept using a vector and space representation. But yeah.
Yes, and no, I don't know. I don't know, and I hadn't read the paper with that question in mind. So there may well be a transformation that's done to the latent space in order to extract the concepts out of it. But that wasn't my reading of the paper. I thought it was baked into the activation of the nodes. Yeah. Which, yeah, I may not be correct on. Now they give another example here too.
Wayne, sorry, there is one more question in the chat. Do they talk about other problems besides classification? I haven't seen it. But...
No, they don't. At this stage, it's only classification.
Okay.
But I think because they say that you can place it in the place of batch normalization, anywhere that you're using batch normalization, you could try this technique. Which led me to one of the questions I have, and that is in transformers you don't use batch normalization, and I think that's due to the fragmented and disjoint nature of words, and so that if you are using normalization at one sample at a time, I'm curious whether you can use this in transformers and language models, but I don't know. Would anyone else have would hazard an opinion on that? No. Okay.
I would have another question, if I may.
Yeah, please.
I was wondering, did they actually test whether this injection of concepts helps with the prediction task to begin with, right? Because you would expect you're sort of guiding the network along in finding useful representations, maybe.
Yes, absolutely.
Does it also helps the end goal?
They didn't. What they did is they took pre-trained networks, they applied an epoch of this to it, and they checked the performance of those networks afterwards, and they were within sort of rounding error of the original network. So they're saying that they did not lose performance, but also they did not say that they gained any performance by doing this.
Okay, thanks.
Yeah.
I mean, on that question of transformers, I'm just thinking that since a transformers sequence has like a variable length usually, I don't know if you could apply a normalization, like a whitening step to an entire sequence each time, because like what would the mean be for a sequence that's a variable length?
Oh, nice point.
But you could do it to the individual word vectors if you were doing it for NLP, for example, probably.
Yes.
Actually, that would, yeah.
Yeah. And then you can start getting the different tenses or meanings of a word. Is it being used as a verb or an adjective? What else was I going to say? Yeah, no, that's good. They did a real life study, a use in a real life piece of work, and to me, this was pleasing, but not as pleasing as I hoped it would be. They used another label that they had in their data set for skin lesion diagnosis. And so part of that, they had these concepts, sorry, this data on some of their data set. So then they produced another data set that then pushed these to particular nodes that they knew about. And then they found that it did help, and that they knew they were important. They then went on and found node 76, which I think is in the auxiliary information. Where's that? Where they found that so they put two concepts in the network. Here they go. And they were trying to find out where, nope, that's not the right one. Okay, so this is they're showing that their concept whitening, that they have disentangled the concepts, which is good. And then they were showing that the concept purity, that's okay. And then they found out, where was it? Distribution, here. So then they started looking at the individual concepts for the individual nodes in a particular layer, I presume, on the 16th layer. And so then they found out that age is quite important, size is quite important. So these are the concepts that they whitened, and then they just ended up with this other node, the 76th node, that was very significant. And they're saying that they might use this to try and find how they want to find a way of automatically detecting which concepts you would like to find, and they're trying to extend this work in that way. And I think they might be using this 76th node and the concept that is related to it to try and find out what it is. And so this is here. Axis, I think here it says that axis 0 and 1 are the two concepts that they were training for, and then the 76 seems to be seems to focus on the borders of the lesion, which I thought was quite interesting. That they did seem to get a concept out of this. Are there any other questions?
Was this the max 76th node? Was that like there was one of the vectors in the Q matrix, the orthogonal matrix, was it associated completely with that node? Was that what that meant?
That is how I'm reading it. Yes.
Okay. So they trained on like 2 concepts or 3 concepts, but the rotation matrix was much larger, and so it discovered concepts as part of the learning process, is what they're saying.
Yes, correct.
Wow.
Yes. And in the process of disentangling, yes. Which I find just fascinating. And whether this is just lucky or whether it's you know, happens in other data sets as well, or whether it is, you know, it is only the most significant concept that this might happen to. Like it might always happen to, say, in images to edges, and then but all the other concepts are just smeared across each other.
One thing I was wondering along those lines is, does the Q matrix have to be like, if your layer before that has 100 nodes, does the Q matrix have to be 100 by 100 matrix? Okay. Like, is it an orthogonal base? Is it, sorry, yeah, does it have to be 100 by 100 matrix?
Again, I don't know. I didn't go through the dimensionalities to that level and the maths to that level. Where I'm just trying to bring it up here.
It must be, right? Otherwise, you would either stretch or compress your space.
Yeah.
Yeah.
So yeah, I imagine so too, but and it is. I mean, Q is a square matrix.
Oh yeah, yeah. So it is 100 by 100.
Yeah.
But in terms of overall added parameters, it's not particularly large, right? So if you have a bigger network, that barely counts for anything.
Yeah, it's quite small.
Yeah.
I feel like the end goal of this would be being able to have neural networks where you can provide some kind of verification of the efficacy of the calculations, or how good the calculations are. And I'm wondering if there's like some kind of vision task that exists that could be like a benchmark for that type of process, or it hasn't been created yet.
Yeah, I like your thinking. Do you mean when you say efficiency, do you mean of the number of the number of calculations of the network, as to how like am I getting the smallest network for a particular task, or do you mean the efficacy in the fact that I can actually show that this node is being useful and how it's being useful in the final classification?
So there's this example that I heard once, which was they trained a network to classify whether someone has skin cancer or not, and it had like a 98% accuracy rate. Yeah. And they thought it was really good. And then they did some analysis like this to figure out what it was concentrating on, and they figured out that it was actually concentrating on the purple marks that patients that were positive for having skin cancer had, because all of the photos were taken right before surgery and they had marked around the lesion. And so I'm thinking more like a verification task where you show like actually the features that it's picking up are good indicators of skin cancer. And so we can say this is something that we would use in a medical, in like an actual medical diagnosis.
For me, yes, I really like what you're thinking there. And for me, it would be something, those kind of situations where you want safety involved, such as driverless cars, whereas you're replaying the data and it's going, well, it could be a person, it could be a person, it could be a person. Oh, it's a plastic bag, I'll drive into it, bang, it was a person. something, in those kinds of layers, in those kind of situations where we want to err on the side of caution, or two, for things like surgery, we want to, you almost want to take that explanation back to the expert and go, the model thinks that it's because it's greater than 10 centimeters, or we've got these purple marks, or, it's reasoning, that then the expert can, with some simple common sense, go, well, no, don't be silly, you're not allowed to use those purple marks.
Mm.
It might also help for other tasks like debiasing, right? So imagine you have a data set, say you have credit data, and you want to take out race, and if you would potentially be able to project in your feature space onto the subset of, say race or gender, and you could maybe cut the network to ignore those nodes afterwards and only work with the space that is orthogonal to it. And so you might get a better trade-off, because I think right now how debiasing works is typically you try to build a model on one of the inside layers to still predict features like race and gender, but essentially you also lose accuracy because there are certain correlations, say, between income, which is of course a very good and useful predictor in credit scoring.
Yes.
But if you could cut down the orthogonal space, and even if there are still correlations, you still might want these, you might get a better accuracy unbiasing trade-off.
I like that, because what you're doing is you're trying to push that characteristic into a particular node. You're trying to concentrate it there, make a very pure node for this, and then remove it out of the network and see what happens.
Yeah.
Or is it, yeah. I like that a lot. Are there any other questions?
One thing I was thinking about when I read this paper is that they're still imposing like this soft constraint on the training process with this second optimization of the concepts. So it's like we want you to create a latent space that's as accurate as possible for classification, but we also want this latent space to be separable using this matrix.
Yes.
So I was just, and then it was curious to me that they like do an update every 20 iterations or something. I was wondering if there was a better way to integrate the two together, or if that was even possible.
The past literature, they have attempted to do that, and they found instability. One of the articles found instability in the in training if you try and disentangle the latent space while training, is what these people say of the last one. So it might be possible, but I think that it will be nuanced as to how it needs to be organized so that it can be effective. I agree with you. It does feel that it's a shame you can't reuse the computation for both tasks.
No more questions?
Don't think so. Any comments or thoughts?
I would just like to see this applied in real life, I guess. Maybe we can discuss at nPlan to see if we can use this kind of approach, because we do actually use not interpretability, but explanations, similar concepts, because we get this question of why is your model making decisions the way it does. And it would be interesting, at least, to see if we can get anything useful out of it. And we are using classification tasks, but not CNNs. So that's also another thing we could consider.
is the so you would be doing this on text, wouldn't you? Natural language processing.
Well, well. So not on the text parts, right? So there are two parts: text and not only text. We also have models that don't work with text.
Okay.
I don't want to give too many details on the record that will go public. But
yeah, no, that's fine.
Obviously, obviously we do have ML models, and interpretations is interesting, and would be also good to see how the concept expands outside CNNs. We spoke briefly about the transformers here, but even the simple MLP, right?
And then also, what else was I going to say? Spacey uses a 5-layer convolutional neural network for named entity recognition, or Spacey 2 did. And so in that way, you might be able to use something like this for those in there. But what would you, so you might be able to then use get explanations on named entity recognition if you know was still being used.
And the example Peter gave is also very, very good about using irrelevant features to learn from.
Yeah.
That's actually, I didn't think of that. That's one thing we should keep an eye also. Cool. Thanks, Dwayne. Very good choice of paper and good discussion. And thanks everyone for the discussions. I'll just give a quick before. Actually, I should stop recording now, and then I can tell a bit more about what we do.